So, you want to bow for this magnificent Herta? Or so I've heard. How quaint. The question is, do you have enough pulls in stock? You don't know? Figures. Very well, this genius self shall explain it to you. Sit up straight and try not to blink too slowly. You see, this entire system you're obsessed with, it's called the pity system. Essentially, if you continue to pull and receive nothing of value, the system feels nothing but pity for you, and eventually, begrudgingly, it hands one shiny 5-star character to you. Yes, even losers get a prize. Isn't that sweet? Don't mistake it for mercy. If you think you are guaranteed to get me when that 5-star drops, how delightful, Yaive. You have a 50% probability of pulling me, the star of the banner, the reason you're here. And the 50% chance to receive, well, let's call it a consolation prize in denial. If you lose that coin toss, you'll need to start over. But don't worry, this time you're guaranteed to get me. But then you ask, Herta, how many pulls do I actually need to get you? 180 pulls. That is the least amount you should prepare before even attempting to pull. But of course you might not spend them all. You might even get me on your first single pull. Or you would need to spend all 90 pulls after 90 pulls, losing the 50-50s. Because that's exactly how the pity system works. Now speaking statistically, how many pulls do you need to get me with a certain certainty? Well then, shall we construct a proper model to describe your inevitable, statistically significant descent into Gacha despair? Ever heard of the Markov Chain? The Markov Chain, or well, the Markov process, is a stochastic process. Stochastic is all about uncertainty, just like how your pull depends entirely on luck. So at any given time, the probability of your next result only depends on your current state, and not your tragic pulling history. Translation: just because you've lost 10 50-50 in a row, doesn't mean the universe owes you anything. We can now define your Gacha state at a certain discrete number of pulls, say n as xn. Now, let me ask you this. How should you define xn? The number of pulls? No, that won't do. The number of pulls you have done is equivalent to the number of steps you took in a Markov chain. Therefore, it is the parameter. Particularly, it is a discrete parameter set. So our Markov chain is a discrete time Markov chain. Obviously, you need to track the number of remaining pulls required in order to guarantee me. Is that not? If you haven't pulled a 5-star in a while, count how many pulls it's been, then subtract from 180. That's your pity countdown. Simple math. Yes, xn is your pity countdown. What does that exactly mean? For any n, if xn equals 180, that means you had 180 remaining pulls required to guarantee me at your end pulls. So on until xn 0 means you had 0 remaining pulls required to guarantee me at your end pulls. In other words, you got me! And here's a bit of trivia. Due to the nature of the pity system, the state xn 0, the moment where you finally got me, is what is called an absorbing state. And what's a hubbing state is a state that once entered cannot be left. Once you get here, the process ends. There's no need to go back. Because really, once you've obtained me, what bar is there to simulate? This particular absorbing state is peculiar since given that you have enough pulls, you are guaranteed to reach the state of xn equals 0 at that amount of pulls. Now we have the discrete state space and parameter space of our Markov chain. Then, how do we assign the probability between states? There are several cases, not states, that might occur on your end poles. First, win 50-50, which means you get me at the nth pole. Congratulations. Second, lose 50-50, which means you get an unfeatured 5-star character at the nth pole. Third, yet to get, which means you have yet to lose 50-50 and have yet to get the featured 5-star character. Fourth, yet to get on guarantee, which means you lose 50-50 and have yet to get the featured 5-star character. Fifth, win on guarantee, which means you get me after lose 50-50. This simple graph illustrates how the transition between states works. States before 90 are where you might lose the 50-50. Hence, you can either move to the next pity countdown, to the state of 90, or immediately to the state of 0. States after 90 means you lost your 50-50. You can only move to the next pity countdown, or to the state of 0. This would prove useful on determining the one-step transition probability of our Markov chain. Now consider this scenario. Your current state at the end pole, or xn, lies somewhere between 180 and 90 to pity countdown. That means the probability that on your next pole, or xn plus 1, you get absolutely nothing but simply drags you one step closer to the pity is 0.99 to 0. This is the case of yet to get. Of course, there's still some chance that the system pities you early. On your next pole, there is a 0.00 for chance. You'll get a 5-star and it's not me. In other words, you just lose the 50-50. How tragic. As for the main prize, you also have a chance of 0.04 that you get me in your next pole. That means you won your 50-50. But do not despair. Deep in your heart, that tiny sliver of possibility is what keeps you clicking, isn't it? Now let's say you got absolutely nothing for your first 89 pulls. Impressive, yet pitiful. That means you are at the state of 91 pity countdown. Your next pull is guaranteed to be a 5-star. Of course, the 50-50 is still there. So the probability for your next pull is distributed as it is. Moving on. If you lose your precious coin flip, now you are in the guaranteed. That means you are now in a state between 90 to pity countdown. Similarly, the probability of you getting nothing on your next pull is 0.99 to 0. Note that this is the case of yet to get on guarantee. Now here's the fun part. If you do get a 5-star, you are guaranteed to get me. That means the probability you get me is equal to the probability of getting all 5 stars, which is 0.006. So let's assume you just spend 179 pity without getting me. A pity indeed. At this point, even the system itself throws up its hands and says fine, just give them the genius already. Your very next pull is guaranteed to be me. That is why the probability is 100%. Then 100% of this process is emotionally damaging. For you anyway. You finally were forced your way into greatness. There it is. The transition probability has been well defined. We let the rows be the starting state, and the columns be the one-step transition state, and each entry of the matrix is the transition probability of the process to start from state row and transition to state column. For example, this entry is the probability to start from state 179 and transition to state 178. We can simply construct a matrix of transition probability. What useful information would you like to get from this model? Of course, how many pulls must you have to get me at a certain probability? Let's say 95%? In other words, how many steps must you take such that the probability that you get me at that amount of steps is 95%? You need to know the average amount of pull required to get me. In other words, what is the average amount of step before you reach the absorbing state of xn equals 0? This is where the famous Chapman Kolmogorov equation comes in. The Chapman-Kolmogorov equation basically says that the probability that starting in state I, the process will go to state J in n plus m transitions through a path, which takes it into state K at the nth transition, and then from state K into state J in additional m transitions. Since the intermediate state K can be any of the possible states, summing over all K yields the desired probability, also known as the law of total probability. If you have even a fraction of my intelligence, you would recognize that you can easily define this as a form of matrix multiplication, particularly the n plus m time matrix multiplication of the transition probability matrix. So the n-step transition probability matrix is just the n-time multiplication of the one-step transition probability matrix. Particularly, we only need to look at the 180th row and 0th column to see the transition probability that you start at requiring 180 pulls to require 0 pull at your nth pulls. Does that make sense? Now weave the calculation to noose. On to the second question. How do we calculate the average amount of pulls you need? Remember about the absorbing state? Since the state 0 is our absorbing state, the average amount of pulls you need is the mean steps of absorption. Let this notation mean the mean time spent in state J starting from state I? Let's assume we start from state 180. The mean steps spent in state 180 is 1 plus the sum of the probability transition from 180 to some state multiplied by the mean steps spent in state 180, starting from those states itself. That one is the first self-visit transition, since the process started from 180. Now the mean steps spent in state 179 is 0 plus the sum of the probability transition from 180 to some state multiplied by the mean steps spent in state 179, starting from those states itself, and so on. Again, this calculation can be simplified by matrix multiplication. If we remove the absorbing state, which is the last row in the last column, we have the transient transition probability matrix. Then we have mu equal to the identity matrix added with the transition probability matrix times mu. Or we simplify as such. Thus the mean steps until absorption is simply the summation of the expected steps spent in all the transient states. Since we start from the state 180, we only need to sum over the first row of the matrix mu. I will leave the calculation to this. Now before you go and start to dedicate your stellar jades to me, why stop at just one me? We can generalize this up to the 6th Eidolon. To fully unlock my 6th Eidolon, you need a total of 7 copies of me. The pity countdown became 180 times 7, which is 1260. Observe that similarly, from state 1260, you can only go to the next pity countdown, to the state of 1170, or the state of 1080, in which you got your first me. And so on until state 0, in which you got me until my 6th Eidolon. By expanding the transition probability matrix into the size of 1260 x 1260, and trivially redefining the state transition probability. The Markov Chain has been formally defined. We can simply calculate our desired quantities. Of course, we can automate all of our calculations. Build a neat little code and let them run. But where's the fun in that? No, this goes for something greater. Now, all seeing presents, go ahead, boost the erudition. I ask you this. How many pulls do they need? You have your answer. So, The question is, do you have enough pulls in stock?